Hey, 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 no. Okay, let's go ahead and get started. I hope you all had a nice weekend. Um, so today we're going to talk about paths, cycles, and trails. So we're going to be looking at kind of subgraphs that have specific properties, and we're going to like prove some results about that. And the goal for kind of the week is to go back to the Königsberg kind of question. So to be able to say when it's possible to traverse all of the edges of a graph. So we will see that theorem on Thursday, and today is kind of like some like setup and background for that. Okay, so we didn't get to the definition of a subgraph last time, so I'll go ahead and do that. It's sort of going to be just what you think it is. So make the following definition. So a subgraph And we saw a lot of vocabulary and new stuff last time, so I'll try and remind you as we go on, like of kind of some of the things that we discussed on the first day. So a subgraph of a graph G is a graph H such that the vertex set of H is a subset of the vertex set of G, and the edge set is also a subset. And furthermore, we want that the assignments of endpoints in the edges of H is the same as in G. And how would we write this? We write just H as a subset of G. Okay, even though we're thinking of it as a subgraph. And we also say G contains H. So you kind of use all the familiar notation and language associated with that. So this is like super common in math, like in linear algebra, you would have seen like a vector space and a subspace. And if you have taken or are taking 1530, then you would have a group and a subgroup. So a lot of times in math, like as soon as you introduce an object, it's also interesting to look at sub objects of that thing. So that's kind of what we're going to be doing today, is looking at graphs inside of other graphs. Okay, so last class we talked about paths and cycles. So we had, just to kind of remind you, paths were graphs that looked like this. And maybe I'll make the edges have a different color than the vertices so that it's easier to see. And we also had cycles. Something that looks like that. And so what we're going to focus on in particular in these next few lectures is subgraphs of a graph that are paths or cycles. So a path in a graph G is a subgraph, which is a path. And similarly for cycles. Maybe I'll write that down. A path in G, or a cycle in G, is a subgraph of G, which is a path. And same thing for cycle. So just to kind of make it concrete, if we had, let's say, this graph here, then a path in this might look like this red set of edges. Okay, so that's like a subgraph that is a path. Okay, are there questions so far? Okay, so now I think the language gets a little bit confusing. So we'll try and like keep this very try and like keep all the language sorted. So we're going to make a definition for talking about different types of paths inside of a graph. So we'll have this definition. So a walk, this is the first thing. So this is not actually a graph. It's just going to be a list of vertex, edge, vertex, edge, vertex, edge that kind of gives you instructions for like how to walk through the graph. So a walk is a list. So V0, E1, V1, and so on up to EK, VK of vertices and edges such that for each I between 1 and K, we have that the endpoints of the edge E are supposed to be the two vertices that are next to it in the list. So the edge E sub I has endpoints V sub I minus 1 and V sub I. Okay, so this is just like kind of instructions for how to go from some vertex V0 to some vertex VK by just like walking through the specified edges and vertices. And then a trail is a walk with no repeated edge. Okay, and then just some notation. So if I want to say that something is a walk, path, or trail in between two vertices, U and V, then I would say I would call it a UV path, walk, or trail. So U comma V path, or alternatively walk slash trail has first vertex U and last vertex V. And those are called the endpoints of the walk, path, or trail. And the other vertices are referred to as the internal vertices. So these are endpoints and the other vertices are called internal vertices. Okay, and then last few things, the length is going to be the number of edges. So in the one I have written down at the top, that would be K. And we say it's closed if the endpoints are the same. So and this would not be a path, so a walk or trail is closed if the endpoints are the same. Okay, so that was a lot. So let's just draw an example and kind of go through some of this. So let's say I have, let's draw this graph. And let me call these A, B, C, D, and X, Y, Z, W, V. Okay, I don't know why I called the edge V, but it's done now. So, okay, so I'll write down a walk, a trail. We'll just kind of like distinguish some of these things. So, for example, a walk might be A, Z, C, Y, D, X, A. So that's an example of a closed walk of length 3. Right, so that starts here and goes this way. It's closed because it starts and ends at the same vertex. It's also a trail because there's no repeated edge. So this is also a trail. If we say we went A, Z, C, V, B, W, A, C, Z. Okay, this is no longer closed because it doesn't start or end at the same vertex, and it's also no longer a trail because wait. Oops, I got these last two backwards. A, Z, C, because it has Z in here twice. So this is not a trail because Z appears twice. And it's also not closed. Okay, is it making sense? Are there questions? This was just an example. Okay, so in a simple graph, so like let's recall a simple graph has no loops or parallel edges. So in a simple graph, we don't actually really need to list the edges because between any two vertices, there's either 0 or 1 edge. So it's not really ambiguous which edge to pick, right? So like, what is one possibility? I could have had 2 edges here. B prime. Okay, so I could have had 2 edges there, and so then I would need to specify that I'm walking along Z and not along V prime. But if it is a simple graph, then you don't need to list the edges, and so you can just you can specify a walk by just listing the vertices, and oftentimes that is done as well. Okay, so what we're gonna do is prove the following statement. We'll prove this lemma. And it's going to say that every UV walk contains a UV path. Okay, so what is the content here? Your walk may use some vertices or edges more than once, and a path would not do that, right? So we're gonna try and see a way to take a walk and inside of it see a path. So let me just draw a picture to illustrate how a walk could not be a path to start with. Okay, so let's say this is U and this is V. Okay, so let's say our walk goes like this. So we go from this vertex to this vertex, and then around here. And back. Okay, so this is like some kind of walk, but then inside of here, there is a way to just have a path that goes from U to V. Okay, instead of taking this whole walk. So does the statement make sense? Okay, so in order to prove this, we're going to need induction. So I'm going to introduce induction briefly now. And in this class, so there's kind of like 2 flavors of induction. There's like regular induction and strong induction, which is a little bit of a misleading name because the 2 are actually equivalent to each other, but we are more often going to use strong induction just because it's kind of simpler for the arguments that appear in graph theory. So I'm gonna introduce strong induction and I'll just like point out what the difference would be for a regular induction. So we're gonna assume the following thing. So we're gonna make the following assumption, which is fairly simple. And it's called the well ordering property for the positive integers. So this is called the well ordering property for positive integers. So we're going to assume that every non-empty subset of the positive integers has a least element. Okay, so this is a pretty innocent sounding statement, and hopefully you're comfortable with assuming that this is true. So this is going to be like kind of the ingredient that we need to make induction work. Are there questions? Okay, so now I'm going to write down a theorem, which is called the strong principle of induction. And then I'll explain how that theorem gives us kind of a recipe for proving statements, and then I'll prove the theorem. So here's what the theorem says. The theorem says, and this is called strong principle of induction. So let's let P of n be a statement with an integer parameter. Okay, so for example, I'll just write an example down here so that you can keep in mind. So P of n might say either n or n plus 1 is even. Okay, so that's an example of a statement. So a sentence that is either true or false that relies on some integer parameter. So like P of 3 would say either 3 or 4 is even. Okay, and that's a true statement. So this theorem pertains to statements that look like this. Okay, so if P of n is a statement with an integer parameter, then if the following two conditions hold, then P of n is true for every positive integer n. So if the following two conditions hold, then P of n is true for every positive integer n. Okay, so the first thing that needs to be true is we need to show that P of 1 is true. Okay, so that's the first kind of ingredient. And then the second one is that we need the following. So for all n greater than 1, the statement P of n, sorry, this should be a K, P of K is true for all k in between 1 and n implies the statement that P of n is true. Okay, so let me break this down a little bit. So what this is saying is, if we can show, so let's just assume that PK is true for all k in between 1 and n. If we can use that assumption to prove that then Pn must also be true, then part 2 is satisfied. Okay, so maybe I'll just comment now, like, so this is the end of the theorem statement. How do we use this as a blueprint for proving things? So if you had a statement about the positive integers that you wanted to show was true for all n, then by the theorem, it suffices to prove that P1 is true, and that's usually called the base case. And then you can, for part 2, you would assume this like red underline statement. This is called the inductive assumption. You would assume this and then use that assumption to prove that Pn is true. Okay, and then step 2 is called the inductive step. So we will see, as an example, the lemma that I wrote previously. So we'll use strong induction to prove this lemma in a moment. But that's kind of like the blueprint for how a proof by strong induction would go. And then let me just comment that, like, what is the difference between this and regular induction? So for regular induction, the inductive assumption just looks a little bit different. You would just assume that Pn minus 1 is true. Okay, so that's like useful in many scenarios, and that's like often enough to get things going. But in graph theory, it's going to be easier for us to assume this. But like I said before, like one is not stronger than the other, really, like they're equivalent. But often for us, it's going to be easier to have this as our inductive assumption. Okay, before I jump into the proof of this, are there questions? Okay, so let's prove this, this theorem. It's actually fairly simple, so it's going to be a proof by contradiction. So let's prove this. So let's suppose that P of n fails for some n. Okay, so it's false somewhere along the way. Then by the well-ordering property, there is a least positive n such that n fails, right? Because let's consider the set of n where P of n is false. By the well-ordering principle here, every non-empty subset of the positive integers has a least element. So let's consider that least element. Okay, so by the well-ordering property, there is a least positive integer n such that P of n fails. Okay, so statement 1 from the theorem statement ensures that n is not equal to 1, right? So 1 ensures that n is not equal to 1. And then we get our contradiction from statement 2. So statement 2 tells me that n, in fact, cannot actually be greater than 1. Okay, so why would that happen? So we said that n was the least, was the smallest number such that p of n fails. So we know that p of k is true for all k in between 1 and n. And that then implies that p of n is true, which is a contradiction with the fact that p of n was meant to be false. So this is our contradiction. And that finishes the proof. Okay, so that was kind of a very brief treatment of strong induction. So in order to illustrate this further and like how we might use this to prove statements, we'll go back and prove the lemma. But before we do that, are there any questions about this? Yeah. Yeah. So this is the proof for this theorem, the strong principle of induction. Good. Other questions? Okay, so let's go back and prove the lemma. So the lemma said that every UV walk contains a UV path. Okay, so we're going to prove this by strong induction on the length L of the UV walk. The proof will be by induction on the length of the walk L. Okay, by the way, let's go back to the statement of strong induction. So in this statement, we started the base case with n equals 1, but this really doesn't matter. Like the number 1 is not significant here. It's just the fact that there is some number for which it is true, and then you're going to argue that it's true forever after that. So when you're making an argument by induction, you should pick your base case to be just whichever number is easiest to prove the base case for. Does that make sense? So oftentimes it'll be 1, but it could also be 0, or maybe it fails for a little bit and then it's true after like n equals 6 or something like that. So you just have to pick this according to what's right for the situation. Okay, so let's do this proof by strong induction. So by the theorem, we just have to show those two ingredients. So the first one is the base case. So think about it for a second. What should the base case be? We want to show that for some length L, every walk of length L contains a path. Yeah. Yeah, so what would happen with a walk of length 1? So we could either, so let's consider L equals 1. So it could be the situation that you go from one vertex to another vertex, or it could be the case that you go from one vertex along a loop back to itself. Okay, so in the first case, this walk already contains a path, right? Because it is a path. So let me just be super explicit here. So let's call this V, W, and E. This one will be V and E. So what is the walk here? It's V, E, W, and here it's V, E, V. Okay, so this walk already contains a path, right? Because V, E, W is a path. What about this walk? How does this contain a path? This is like kind of a trick question. So just the vertex V by itself is a path. So I would change this for just the walk V, and now that's a path. Does that make sense? So this is satisfactory for the base case. We've shown that if a walk has length 1, then it contains a path. Another thing that you could do for the base case is take length 0, which is like maybe even easier because the only walk of length 0 is just a single vertex, which is already a path. So that's like another option for the base case. So I'll just say alternatively, we could take L equals 0 and then a walk of length 0 is already a path. Okay, so does the base case make sense? Are there questions? Okay, so now we're gonna do the induction step. So part 2. So this is for L greater than 1. So we're gonna assume the inductive hypothesis. So let's assume that all walks of length less than L contain a path. Okay, and then we're going to use that assumption to prove that a walk of length L contains a path. So let's let W be a walk of length L. Okay, so there's going to be kind of two cases. So what is the issue with a walk? Like in what scenario could a walk not be a path? It's when it has a repeated vertex, right? If all of the vertices are distinct, then your walk is already a path. So we're gonna just deal with that case separately. So if W has no repeated vertex, then it is a path. So we're done, okay? If there is a repeated vertex, okay, so what am I going to try and do? My goal is to take W and make kind of a shorter UV walk and then apply the inductive assumption. So let's just draw maybe a picture. So let's say this is U and this is V, and then my walk W looks something like this. Okay, so we have this repeated vertex. This appears twice. in the walk. So what I'm going to do is just delete all the edges and vertices in between the appearances of that vertex. Let's call this thing W. So I'm going to delete from W everything that appears between the two occurrences of W. Okay, so in our example, how would this look? So I'm going to call this, let's say, Z1, Z2, Z3, Z4. Okay, this is a simple graph, so I'm going to omit the edges when I write down this walk. So my walk W is U, Z1, W, Z2, Z3, Z4, W, V. Okay, I'm gonna delete everything in here. And I also need to leave behind just one W, so I'm also gonna delete a W. So that leaves me with just U, Z1, W. I'm skipping everything all the way up to V. Okay, so what has this left us with? This is now a shorter UV walk. So, okay, it could have been, in this case, it is a path already, but it could have been that there was another little detour over here or something like that, right? So this could just leave us with a walk and not a path. So this is a shorter UV walk, which is contained in W. And then by the inductive hypothesis, since this is a walk that has length less than L, it contains a UV path P. This new walk contains a UV path P, which is contained in W. Okay, so going back to our example, if our original walk like traversed this way around that triangle through here around this square and then ended up back at V, we observed that we had W in here twice. So then we get a new walk, which is shorter, right? This thing. And then by the inductive hypothesis, that shorter walk itself contains a path, which would be this path. And that path is contained in the original walk W. Yeah, do you have a question?
You do the same group just by like removing B to make a shorter path and then adding it back on.
Removing, yeah, okay, so the suggestion is like, what if we just delete, oh, okay, but here's the thing. So we're trying to get a walk from U to V into a path from U to V. So if you delete V off the end, then you no longer have a path from.
If you say like our walk as like a list of vertices and then you have like V minus one and then V, then you have a path from U to V minus one. You just put V at the end.
I think you could have a situation where sticking on that extra edge, like let's say this is U and this is V. So here's what I'm worried about. If you add back in the edge, could you accidentally make it into a cycle? I think that could happen, but I'm having a hard time. So let's say we went from U to V to this vertex back to V. And you're saying delete this edge, right? The remaining thing is already a path. But then adding back in this edge doesn't get me a path from U to V.
Like you do the same thing, but just like only including the walk from U to the first occurrence of V.
Maybe. I think that could work. Yeah. Yeah, good. Okay, other questions? Yeah.
You have to use induction to prove it. It would just like use the logic we did to make it shorter till we just have like till we don't have any reoccurrence of vertices, and then it's just like a path because there is no reoccurrence without using induction.
I think that maybe so you're saying like structure the argument as follows, like start with your walk. If you ever have a repeated vertex, delete the stuff that's in between those two. And then just do that again as needed in order to. I think that does work. I think the only advantage in this is just maybe a little bit in like the clarity of like you only have to do the step one time to like reduce it to something that's true. But I think what you're saying also works. Yeah. Yeah. Yeah, so U and V have to be distinct because if you have, it wouldn't be a path, right? Yeah. Because paths have like all distinct vertices. Good. Other questions? Yeah.
Our goal is to just like shorten the walk so we can even better hypothesis. Like do we have to like delete like the repeated vertex? Like I'm trying to just delete like just like vertex like maybe. But that would also like shorten the walk.
So like in this example with this one, what would you have deleted?
Z4 to Z2, like if we just do like Z3 in between, we go directly from Z4 to Z2, and we're also like shortening that path.
Okay, yeah, but it's possible that like this isn't an edge in your graph. Yeah. Yeah, good question. Okay, other questions? Okay, so we're gonna now talk about something called connectivity. So we talked about last time what it meant for a graph to be connected, and now we'll just go a little bit deeper into that and develop some language to talk about connected graphs and like to look at graphs that aren't connected. Okay, so recall from last time that we said a graph was connected if for every pair of vertices U and V in the graph, there's a path from one vertex to the other vertex. Is this ringing a bell? So we'll also say like, yeah, maybe this is worth writing down because this language I think has potential to be confusing. So we'll say a vertex U is connected to V if there's a path from U to V. So why do I say that this could be confusing? Because this does not mean U and V share an edge, right? So it's like maybe intuitively something you might say. If U and V shared an edge, you might say they're connected. But this This just means that there's a path from one to the other. Okay. Okay, so now I'm gonna make a definition. So the components of a graph G are going to be the maximal connected subgraphs. Okay, so I'll draw an example. So like, let's say this is our graph G. Make another little. Okay, so let's say this is our graph G. So what are the components? So these are the maximal connected subgraphs. So like, for example, this is one component, this is one component, this is a component, and this is a component. And we'll say that a component is trivial if it has no edges, and that's also called an isolated vertex. This is trivial / isolated vertex. Okay, does this make sense for what components are? So let me just make an observation. So let's say I add an edge to this graph. So it could happen that the edge I add is just inside of one component. And so that would preserve the total number of components. But another thing that could happen is I add an edge that goes in between two components, and that would have the effect of reducing the number of components by 1. So adding edges either decreases the number of components by 1 or 0, right? So that gives us the following proposition. Just about kind of relating the number of vertices, edges, and components. So it says that every graph with n vertices and k edges has at least n minus k components. Okay, so let's prove this quickly. So for the proof, so if I have a graph with n vertices and no edges, that has n components, right? Each component is just an isolated vertex. And by the observation that we just made, adding an edge will reduce the number of components by at most 1. So when I add k edges, then it will reduce the number of components by at most k. So that means that the number of components has to be at least n minus k. Does that make sense? Maybe I won't write anything for that. So this is like kind of just by that reasoning of like what does adding an edge do? Okay, so that's like kind of the effect on adding an edge, but deleting or adding a vertex could do something more dramatic to the graph. So let's look at what happens when we delete vertices. So I'll make a definition. Oops. So, okay, so yeah, so how do we delete a vertex from a graph? If I delete a vertex, then I'm also going to delete all of the edges incident to that vertex. right? So I'll call something a cut edge or a cut vertex of a graph. If the deletion of that edge or vertex increases the number of components. And how would we write this? So how you would just write G minus E or G minus V to denote the graph with the corresponding edge or vertex deleted. So let me draw two like pictures. So one is of a cut edge, right? So this edge is a cut edge because if I delete it, then I increase the number of components. And similarly, so like here's kind of like the most dramatic thing that can happen with a vertex. Like let's say I have a bipartite graph with like one vertex on one side and then a bunch of vertices on the other side. If I delete this vertex, then I also delete all the edges incident to it. And so then I'm left with just 4 isolated vertices on the right. So that increases the number of components quite dramatically. And so that's a cut vertex. Okay, and then another thing is an induced subgraph. So this is going to be a subgraph obtained by deleting a set of vertices. And this is how you would write it. So if I want to look at the subgraph that, okay, yeah, so I would just write, so like let's say T is a subset of the vertices, then I would write G brackets T for the graph G minus the complement of those vertices. So like in this example, the 4 isolated vertices are an induced subgraph. And that induced subgraph is G of those vertices. Does that make sense? Okay, so we're gonna prove a theorem about cut edges. So what I want to do is be able to say when an edge is a cut edge or not. Does anyone have a prediction about when something is a cut edge or like what a condition might be? So like, let's look at something like, for example, this edge. Is this a cut edge? Why? Yeah.
Is it because it's part of the cycle?
Yeah, so like it's part of a cycle, right? So kind of intuitively, like this edge didn't really separate these two vertices because there's just another way to get from that vertex to the other vertex. So that's exactly what this theorem says. So here's the statement of the theorem. So it says that an edge is a cut edge if and only if it belongs to no cycle. Okay, does the statement make sense? Okay, so let's prove this. So I'm going to let E be an edge in a graph G. And let's call the endpoints X and Y. And I'm going to let H be the component containing E. So this argument like won't depend heavily on whether or not the graph G is connected. So we're just going to focus on whichever the connected component is that contains that edge. And so we'll let H be the component containing the edge E. So since the deletion of E doesn't affect any other component, it suffices to show that H minus E is connected if and only if E belongs to a cycle in H. Okay, so this entire argument we're just going to look at inside of the graph H. Okay, so let's suppose, so right, this is an if and only if, so we have to prove both directions. So first, let's suppose that H minus E is connected. So then we need to prove that E belongs to a cycle. Okay, so I'm going to give you a few minutes to think about how to prove this direction, and then we'll discuss. Okay, so how should this part of the proof go? How do we get the cycle? So we know that H minus E is connected. So yeah,
Since H minus E is connected, and X, Y are two vertices, like any vertices, you can make a path from X to Y.
yeah.
And then, since there's a path from X to Y, if you like add it back in E, yeah, since E, has the endpoints X, Y, you can create a cycle.
Exactly. So, right. So what does connected mean? It means that I have a path between any two vertices of my choosing, right? So if I have my edge E with endpoints X and Y, and I'm saying that H minus E is connected, so Maybe there's like some other stuff going on here. I know that there's a path from X to Y, right? And then adding back in that edge E would give me a cycle. So since H minus E is connected, there is a path from X to Y, and adding E to this gives a cycle. Okay, are there questions about this part? Okay, so now we'll do the other direction, which I think is like a little bit more the tricky one, just because now we're going to suppose that E belongs to a cycle. C, and we now have to show that H minus E is connected, which means that we need to show that for any pair of vertices, there's a path between them inside of H minus E. I'm going to show H minus E is connected. Okay, so let's let U and V be vertices in H. Right, so these are two vertices of H minus E. And we want to show that there's going to be a path in H minus E between them. So we know already that the component H is connected. So since H is connected, there is a path P from U to V inside of H. So H has a U, V path, which I'll call P. Okay, so maybe I should draw a picture just to keep everything straight. So, okay, so let's say this is U, this is V, X, Y. This is our edge E. E is contained in a cycle called C. And then we also have a path from U to V. Okay, so this is kind of the setup. Okay, so actually, let me just first draw this path differently. So if the path does not contain E, then already this is a path in H minus E that connects U to V, right? So if my path looks like this, then this is also a path in H minus E. So we're good. So case one, if P does not contain E, then P is a UV path in H minus E. So we're done. Okay, then the more complicated case, if P does contain E, so here's how the picture would look in that case. So we have U, V, X, Y, E. And then let's say P is this red path. Okay, so what should we do instead? How do we get a path from U to V that does not go through E? Yeah,
Walk the other way around the cycle.
Yeah.
On the path.
yeah, exactly. So like basically the cycle means we have two options, right? We could go the way that went through E, or we need to go the other way. So here's how we're going to do that. So let's consider the walk where we replace E and P with the rest of the cycle. So E in P with the rest of the cycle. Okay, so we started with P, which was from U to X to Y to V. That went through this edge E, which is XY. And so what I'm going to do is replace E with going around the cycle the other way. So this will become UX. And then, okay, we're not going to cross E. We're going to go back the other way around the cycle. So we'll go back to U and then to Y and then to V. Okay, does that make sense? So this is a walk, right? And we proved that walks contain paths. So this walk contains a path, which is contained H minus E. Okay, so in the path, we would forget about the fact that we first started at U, went to X, turned around, and then went through Y. We would just, so the path inside of this walk would just go from U to Y to X. Or sorry, U, Y, V. Does that make sense? Yeah. A path. Yeah. So, okay, yeah. So what have we done? We picked an arbitrary pair of vertices and we showed that they were connected by a path. And so that tells me that H minus E is connected. So that completes the proof. Okay, so I'm gonna prove one more thing and then we'll stop there. So I'll say a walk is odd or even if its length is odd or even. Okay, so if the walk has odd length, then we'll say it's an odd walk. Okay, and here's a lemma that we'll use next time. So the lemma says that every closed odd walk contains an odd cycle. Okay, so why is this interesting? So the statement is not true for even walks because like what could my even walk look like? I could start at a vertex, go to a different vertex, and come back along the same edge. That would be an even closed walk, but it doesn't contain a cycle. So this is just like to illustrate the fact that like this lemma is like actually saying something, like it has content. Does that make sense? So the same statement does not hold for even walks. Okay, so let's prove this, and we're gonna prove it again by induction on the length of the walk. And we'll call that length L. Okay, so what should our base case be? So I can't take L equals 0 because that's an even number. So we're only going to do the odd numbers. So what happens when L is 1? What is a closed walk of length 1? How does that look? Yeah.
Like the loop, like where it's out.
Yeah, so a closed walk of length 1 is a loop, which just looks like that. And that is a cycle of length 1. Okay, so now we'll do the induction step. So for this, we need to assume the inductive hypothesis. So we'll assume the claim holds for odd walks that are shorter than W. Anyway, I think I need to say more here. So let's I'm gonna scoot this down. Let's let W be an odd walk of length L, which is strictly greater than 1. And we'll assume that the claim holds for odd walks shorter than W. We also want it to be closed. Okay, so we want to prove that W contains an odd cycle. So one thing that could happen is if W has no repeated vertex other than the first vertex equaling the last vertex, right? Then already W is a cycle, right? So case 1 is that if, and this is going to be kind of similar to the proof that we saw before. So if W has no repeated vertex other than first equals last, then W is already an odd cycle. Okay, do you all agree with this so far? So then, if a vertex is repeated, then let's do the following. So let's say this vertex V is repeated. We've got some stuff going on over here. And maybe we have an additional like detour over here. Okay, so let's say this is our vertex V that's repeated. Okay, so we're going to view W as starting at V and ending at V, and then we're going to break W into 2 VV walks. So I'm going to break W into 2 VV walks. So in this picture, we'd have part 1 on the right and part 2 on the left. Since W has odd length, one of the two has to also have odd length, right? I can't break it into 2 even pieces. So since W is odd, one of these is also odd. And it is also shorter than W, right? Because we took out a chunk. And it's shorter. Than W. Okay, so then we win by the inductive hypothesis because we're assuming that any odd walk of length shorter than W contains an odd cycle. So in this picture, it would be this one. So that finishes the proof. By the inductive hypothesis, this contains an odd cycle. Okay, so that finishes the proof. Okay, so I know like right now this first section feels a little bit random. So next time, like all of this is building towards kind of our solution to the Königsberg Bridge problem. And also I think like part of the point of this chapter 1 is to kind of just like lay out a lot of the definitions and terminology that we'll be using throughout the semester, and also familiarizing you with the techniques. So like the technique that we saw in this lecture was proof by induction. And then in the next lecture, we'll get a little bit into like some counting argument stuff, which is like another technique that comes up pretty often. So, so yeah, I'll see you all on Thursday, and the first office hours are today.